We're talking about rocket propulsion, and so I want to set up a coordinate system, and this is a perfect example of a variable mass problem, one of the very fun variable mass problems you do. And the setup, before I go and set up everything up, is that you have a rocket that burns fuel, and so there's a constant thrust force which exerts. Basically, the model is that you have a mass that is decreasing its value with a constant force. So this force is constant, but the mass is decreasing. So, F equals ma then says that the acceleration, if the mass goes down, the acceleration goes up. And so Newton's laws aren't that great to work with, especially because the acceleration is dependent on the mass. Okay, and so you got this weird dependence of the acceleration being a constant divided by the mass, which is a function. Maybe it's a function of time, maybe it's a function of position, maybe it's a function of velocity. And so kinematic equations don't technically hold, especially the ones for constant acceleration. So we can't do that, but we can use momentum. And so let me set up the picture and set up all the symbols that we'll be using. Okay, I'm going to draw a nice big coordinate system. X-axis. We're going to start. I'll draw the picture, kind of, just give you some idea. So we got to start off with this rocket. This is my rocket. And let's say it starts off filled with fuel, right? Anyone who knows more about rockets than me knows that the fuel isn't actually in the rocket. It's in like the big things that they carry with it. But anyway, so let's define some symbols. Obviously, we're in the X coordinate system, which is important, by the way. And this coordinate system has at rest attached to like some reference frame. This is also deep space. So gravity is 0. Now, is gravity 0 in space? No. I mean, even for the International Space Station, gravity is still pulling down with this magnitude of like 9.79 meters per second squared. That's a different phenomenon of weightlessness when you're orbiting, but I'm talking about deep space, far enough away from planets, stars, other galaxies, so that the local gravitational acceleration for an object at quote unquote rest there is 0. So that's what deep space means. So gravity is 0. So let's define some symbols for this. We got fuel and we got the rocket, right? And that's the total mass. So the total mass it's a function of time. It's equal to the mass of the rocket, let's be as explicit as we can, plus the mass of the fuel. The easiest thing to say is that the mass of the fuel as a function of time, m subscript f of t, it's the starting mass of the fuel, m0, minus capital R times time. If you look at R, it has units of dm over dt. It's a fuel rate. It's a rate of burning fuel, right? And this fuel in liquid form is being converted into a gas and then thrown out of the chamber. And the gas then propels the rocket forward as it's being thrown out. So it has the units of kilograms per second. The R is set by the engine. I mean, the engineers just set everything, and you can actually relate the thrust force to the rate of the fuel burn times the exhaust speed. Now, this exhaust speed, right, it's the speed that the gas is shot out of the rocket in the reference frame of the rocket. And so as the rocket's moving along, no matter if it's moving in the fixed coordinate system or not, the rocket has obviously, and I'm going to erase this in a minute, its own coordinate system, xr. And so Vex, exhaust velocity, lives in this coordinate system, the one down here. Okay, but we're actually going to be doing momentum in this coordinate system. So there's going to be a slight change of reference frame that we need to address. And we will do that as we set the thing up. Okay, so again, the force is constant, but the acceleration is variable. And since it's an acceleration, strange one is a function of time, and it's a function of mass, then momentum is best suited for that. Okay, so let's draw a generic location that we're at. Let's say we're at some value x. I'm going to just give me 5 seconds. I'm going to delete this just to give myself more space. But the mass of the rocket itself with empty fuel is denoted m sub r. And the mass of the fuel is denoted m sub f. So just above here, m sub r plus m sub f. Right? And m sub 0 is the initial amount of fuel in the rocket or in the tank. So let's go to, so this is how these derivations go. We're trying to find an equation for really the velocity as a function of mass, which we can then turn into a function of time. So at a generic location, x, that's how this stuff works. We have the rocket, it's got some speed v and mass m, which again, I'm saying that lowercase m is mr, the constant, plus the time varying fuel, just to keep the notation clean, and then we'll revert back. Okay, so during this course, there's that thrust force. So at the next instant in time, the rocket is at a location x plus dx, which doesn't really matter. Its speed will increase, so it'll be v plus dv, but the mass has gone down, so it's now an m plus dm. So the mass, and we know that the velocity or the mass goes down, but we say that it's m plus dm to be sort of theoretically show that the change in the mass is fixed inside the dm. Where does the mass go? Well, it's shot outward. Let's see, I'm going to delete that v right there and make a little bit more room. So yeah, this is the rocket as initial speed v. After it ejects some fuel, it's got a velocity v plus dv, but now we have this minus this little packet of fuel. What's this velocity now? That's where we go back to this reference frame, okay? In the coordinate system of the rocket, the velocity of the exhaust points to the left. But from our stuff about reference frame, the velocity of the ejected fuel, for lack of a better notation, with respect to the ground frame, or maybe the laboratory frame, is the velocity of the fuel with respect to the rocket plus the velocity of the rocket with respect to the ground frame or lab frame. Now, there's no absolute coordinate system in space, and so you have to be clear that you're watching. It's like a distant planet, and the planet is more or less at rest with respect to the moving rocket. Maybe you're in the galactic frame. Galaxy, let's just say that G is galaxy. Okay, so the term on the left is what we want to put into here, this arrow pointing to the left. And let's be clear then, the velocity of the fuel relative to the rocket is minus VEX, right? Because it points to the left when the coordinate system of the rocket points to the right. The velocity of the rocket with respect to the ground is, of course, just the typical V. And so that means that the fuel in the galactic frame, as we're watching the rocket propel to the right, the velocity that's exhausted is V minus V exhaust. So hopefully that makes sense of the reference frame. And that's exactly what we have in our results. So we even have to do a little bit of reference frame stuff. And because if you just put V exhaust, you're going to get the wrong answer. All that to say, the last the last little thing to include is that if the rocket increased by a mass equal to dm, then this little piece has mass minus dm. The dm is less than 0, and so we're calling that little chunk minus dm. So there's all these negative signs to sort out with, but I hope I did a good job of explaining them. Certainly the textbook goes through that explanation as well. So now that we're done with these reference frames, we're only going to work now in the reference frame of the galaxy. I'm going to call it that. So I'm going to delete all this other stuff down here. If I delete a T, I'll just rewrite it. I got just about everything besides that little line. Okay. So give me just a minute and we'll continue. Good. Now we can do momentum. Now that we've set up our coordinate system, we set up our problem, this is a mini explosion. It's an infinitesimal explosion that's always constantly happening. And so what's the conservation momentum for this? Well, it's the m times v. That's the initial momentum of the system. The system is that rocket plus that tiny little packet of fuel in that time dt as it goes a distance dx. You got to be really comfortable with working with these differentials in later classes too, because it shows up a lot. So initial momentum is mv. What's final momentum? Now that we've done the work on the back end, we just look at the stuff and write it down. So the initial momentum of the rocket and the fuel at initial speed v is going to equal the final momentum of the rocket with the increased speed and lower mass with the ejected fuel moving in the other direction. So we have mv equals the momentum of the rocket, m plus dm times v plus dv. And then plus another momentum, which is minus dm times v minus v exhaust. It doesn't matter. It doesn't matter that the dm comes second, technically, but in the spirit, always put dm on the far right-hand side when you're ever doing stuff like this, because you eventually want to integrate, and the only other place the dm might be that's not at the far right would be over like a numerator. DM's, well, sometimes the dx, sometimes it comes first. Let's just stick with what the book has. So now we can look at plenty of things that can cancel. Well, let's factor everything out first. So foiling that first term gives us mv plus m dv. Again, m and v are both functions of time, plus v dm plus dm dv, running out of room. So I'm just going to make more room. And then you can finish it up. Let me select this and I'll drag it. I believe I can just drag it. Okay, so moving on, I'll continue that now. It looks like the T and the M kind of got smushed, sorry. Okay, so we got MV, I'll just rewrite it down here. We got MV equals MV plus MDV plus VDM plus DMDV. Now, minus VDM plus V exhaust DM. So that is us factoring everything out. So this is how conservation momentum works. And so now you can see that there's the parade of cancellations. The MV and the MV can cancel. The VDMs can cancel. maybe just 2 lines to the left, that way we don't, okay. There's nothing that has a pair of cancellations, although I do want to just briefly mention that this term, dmdv, is also 0. That's because when you're dealing with differentials, if, you know, the differential is quote unquote infinitely small, technically the square of the differential is infinitely small. So it's 0 when compared to the infinitely small thing. Another reason that might be perhaps a little bit better might be considering like how computers calculate things. The computer doesn't know what a real number is, so you have to give it some sort of tolerance. And in most systems, certainly in MATLAB, the number system that they use is the number, they start with the number 1, and the next number is 1 plus 10 to the negative 16, a tiny little number. So that's, you know, 1.15 zeros and then 1. And then the next number is 1 plus 2 times 10 to the negative 16. So you have 1 point and then 16 zeros. Then you have 1.15 zeros 1, 1.15 zeros 2, 1.15 zeros 3. And that's called floating point numbers. So the dx in MATLAB is 10 to the negative 16 officially. So if you're doing a problem and you encounter like a dx squared, well, that's 10 to the negative 32. You know, although you can enter in something called 10 to the negative 32 in MATLAB, the numbers will not recognize anything between 1 times 10 to the negative 1 plus 10 to the negative 16 between 1 and 1 plus 2 10 to the negative 16. So basically, okay, that's the one time I'll draw it, get my point across. You know, 1.1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, and then all those repeated, dot, 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 0, 2. Well, there can't be a difference of more than 10 to the negative 16 between these two numbers. If it's like 10 to the negative 17, then the computer doesn't count that as an actual number, because the computer can't handle infinitely many numbers. And so you got to decide where to stop somewhere. And most computers choose 10 to the negative 16 because it's very helpful with how they store the data. So that's why we're going to drop that term. Anyone who's interested might look up something in their class, like maybe in their digital computations class on machine arithmetic, because that's what computers actually do. So that also term goes away. That's a little bit of an aside, but I think an important one. What's left? We have 0 equals MDV plus V exhaust DM. What are we going to do with that? We have now a way to set up sort of an equation to get an expression of velocity as a function of mass. Because again, ultimately, we'd like to use momentum to find, you know, position versus time, velocity versus time, acceleration versus time, all the quantities at every point in time. So the way I would do it is get the V. So I would manipulate this so you get dV equals minus constant, that's a constant, times dm over m. And now I can integrate. We've separated variables. Again, that V exhaust is constant. So we have basically everything with variable V on the left side, everything with variable M on the right side. And so we can integrate both sides. The coordinate that we would use would be the time. So this is initial velocity, which is 0. And so this is going to be our velocity at some time. We're going to use the dummy variable. What are the limits of integration for here? The starting value, which is mass of the rocket plus mass of the fuel, what is the limit of the integral upper limit that I can't barely fit into there? The upper limit should be mass of the rocket plus mass of the, plus initial mass of the fuel minus RT. That's what the upper limit should be. And there's also that minus sign. So I'm going a little bit further than the book goes because I'm including the time value right there. Because both of these technically are functions of time. So the left side is V, of course. What's the right side then? It's just the left side is just V minus 0. So V, technically is a function of T. Oops. Equals technically minus Vx, V exhaust times natural log of M from those limits. Okay, and since I'm running out of room, I'm going to go ahead and delete that, but include the limits and rewrite it as a function, velocity as a function of T. By the way, the negative in front of the V exhaust flips the natural log. That is, it flips the limits because you have what? Natural log minus natural log of x equals natural log of 1 of x. I don't have time to go into the picture behind that, but that's the property of logs. And so it's really natural log of 1 over m between those limits. So basically the final result is that we have V of t equals exhaust velocity times natural log of what? This is going to be initial mass, so mass of the rocket plus initial mass of the fuel divided by mass of the rocket plus initial mass of the fuel minus RT. And so we get an expression for the velocity as a function of time. The book only goes so far as to give a velocity as a function of mass, but you can see that we just added in the function of mass as time to get this result. And so what does this look like? If you graph velocity as a function of time, well, what is this? Where is this function defined? I mean, a simple kind of algebra problem shows that at time t equals the total mass divided by burn rate, you should have m equals 0. And so certainly the mass as a function of time goes like this, right? So that time t is initial mass over the rate. But what about the velocity? I'm going to use this space to draw it right here. The velocity graph, it's like log of 1 over minus t. So what does that look like? Well, if the mass was constant, it would just slope up linearly. The slope of that would be acceleration, which would be thrust over constant mass. But since mass is decreasing, the velocity, which starts at the same point, is always going to be increasing at greater than linear. If you take log of like 1 over x or something, well, log of 1 over 1 minus x rather, you're going to get a shape like that because it starts at 0 at x equals 0, and then at x equals 1, we get to a final value. Well, it'd be defined for less than 1. We get to a final cutoff value where the fuel runs out, and that's at that same time m naught over r. And after that, then rocket just coasts at constant velocity until something else happens. Maybe it gets caught in some gravitational field or something and then starts accelerating. So that is the rocket propulsion derivation. It's a great example of how conservation momentum can be used to derive the kinematics of an object with a variable mass.